So these are the people who are present. Very few. Aman, Veera, Bhagyashree, Chinmay, Krishna, Keo, Rashid, Nigam, Noor, Priyanka, Raman, Soumya, and rest 23 have difficulty in joining or what, I don't know. Okay, anyway, I'll start. I don't know what these people are doing at 11 in the morning. What's the problem? At 7 in the morning, I can understand. Sometimes you. Okay, so without wasting much time on that, why some people join, while some others do not, let's carry on with this. Quantum mechanics. Okay, my typos error is there. Anyway, so we are going to talk about atoms which have more than one electrons. Many electron atoms. We can also say multi-electronic systems. So, in the last class, I also told you that beyond hydrogen atoms, we do not have exact solutions. So, and there are certain things, there's a method. You have to apply a technique of approximation. And one of the techniques that we are going to use is for this particular purpose is orbital approximation, where we consider each of the electron, like let's consider the simplest, when we move away from moving forward, hydrogen के बाद क्या आता है? Helium. So let's imagine a helium atom. It has two protons. So the effect of two protons on one electron, electron number 1, that you consider first. You also, in a similar way, you also calculate and try to understand the effect of that two protons on electron number 2. So basically you know the structure of hydrogen atom and treating each of the electron with interacting with multiple protons at the nucleus. So that's how, so that kind of interaction can be easily imagined, and we try to apply the same concept that we apply for hydrogen atoms. And then we move, we for a moment assume that electrons are, if they are not interacting with each other, this could be the solutions. And then we add few things that we, the perturbation that I talked about, the electrons will start interacting, and then you have to take into account that fact. So all these things, when you take it together, you are able to understand the thing. So basic idea is that uh, so I remember when we discussed hydrogen atom, we started with spectroscopy. We started with quantum mechanics with introduction to spectroscopy, that hydrogen thing. And when I ended hydrogen atom, I ended with spectroscopy. What is the current understanding, right? So spectroscopy is the starting point in all these things. You cannot see an atom, you cannot see an electron and proton, how they are arranged, but you can get the idea about their energy, their momentum through spectroscopy. And that is your, so spectroscopy becomes your eyes to understand the location, the energy of the uh, so somebody is knocking. Somebody trying to get in. No. Okay, so basically spectroscopy is the key to understanding these things. So now you know, you learned the selection rules, which are nothing but uh, uh, um, they are just, they tell you how you can conserve the angular momentum, how you can generate the dipole, electrical dipole. So if during certain transition these two things are happening, that transition will occur. Simple. and that is true for any molecular transition, atomic transition, everything, right? Conservation of angular momentum, and in that emergence, the creation of that dipole during the transition, which we now know as transition dipole. So electric dipole interact. So that is the crucial thing, and that spectroscopy, lines appearing in the spectrum either in absorption or emission, that tells you about सुष्मिता रानी. which email is she using? दो email तो इसका मैंने डाला हुआ है उसी में इन्विटेशन में. तीसरा email यूज करती है क्या? Okay, so that's thing. So is so this so which photon is emitted or absorbed, that is decided by this h mu is equal to del E, and so you can calculate the frequency that of photon that's needed for absorption, or which will be emitted, the photon's frequency that will be emitted if it is a emission spectrum. So that these spectrum gives you information about the energy of electrons in atom and energy related to momentum. So momentum can tell you about the uh, your velocity, and so that's how you are able to code it. So wave function is the main thing that we have been saying all along. We have been visualizing the electron as a standing wave, and when there are more than one electrons, we can write wave function for each one of them. Okay, and then we can express the overall wave function as a combination of, so if you have one electron 1, you have so you can, so it is like if you have a number of electron, you have nucleus which is having lots of protons. So suppose protons are there, and then you have electron at distance, electron number 1, another electron here. So then you can show this distance as r1, you can show this distance as r2. So electron number 1, electron number 2, each one behaving as wave, and superposition of all these waves you can represent as the total wave function. So you write a wave function for psi for an electron as a combination of all these together. You write a total wave function summing up for all the electrons that are present in the atom. Okay, so that is the wave function corresponding to position r1 for the electron 1, electron number 1, corresponding to electron number 2 at a distance r2, and so on. So that's how you pictorially you can imagine that imagine it, and then start writing the equation, the wave function. So in this case, we think of an electron occupying its own orbital, and mm, we of that electron occupying a certain. So that's how. So that's what I was, the picture that I just drawn, जो मैंने अभी just draw किया थोड़ी देर पहले, उसी तरह से for electron number 1. So electron 1 for electron 2 at r1 at r2, and so on, like this electron. So when you are imagining uh, these electrons are in different circles, and for a moment let's imagine that way, and then you can calculate the distance r1, r2, and so on. So this is how you can think of, write all the individual wave function, and then when you multiply them together you can get it like this. So this is what you have been in the fundamental postulates of quantum mechanics that you have been learning. You have learned this thing that you can express a wave function as a sum of several wave functions. So this is the total wave function, right? This one is the total wave function, and this is the wave function of electron at electron number 1, 2 and 3, so at a distance r1, at distance r2, and at r3, and so on in this manner. So individually we have to think of each one of them as just like the electron is in a hydrogen atom, the difference being that now there are more protons, so the interact z has changed. So then we write the product, and yeah, so that's what we say, that we think of individual orbitals as the one resembling the hydrogenic orbitals, just hydrogen like orbitals, the way we have imagined everything. We try to keep things simple, and take into account the corresponding nuclear charges. So helium it is 2, lithium it will be 3, and so on. So one electron at a time interacting with the nuclear charge at the center. So we write the wave functions, and then later on modify it when we realize that these electrons are interacting with each other, and then it gives you the overall picture. So this is only an approximation, I told you, and so uh, your approximation is good if it is able to come closer to the real picture. So this the discussion will tell you what happens next. So this is your starting point for understanding the atomic structures of all these multi-electronic systems, and so what we are talking about approximation here. Electron number 1, just like we considered in isolation interacting with the nucleus, electron number 2, we again think of that electron at a distance r2 interacting with the nucleus. So this is so we basically we are treating them hydrogen like beings, hydrogen like atoms, hydrogenic atoms, the orbitals that were there in hydrogen like atoms, one electron system, one at a time, and then we are combining them together. But however, we have not yet thought about if what could be uh, there is a possibility. So that is under the assumption that there is no interaction between the electrons. That would have been true, perfectly true. We could have got the exact solution if the two electrons E1, E2, E3 are not interacting at all. But in reality, they start interacting, there is repulsion, and that gives rise to many more things. We'll see that later. So later on we talk about shielding, penetration. These all things apply. So electron repulsion arising from that. So now electron number 1, electron number 2. These are two electrons in, say, in hydrogen helium atom, the first multi-electronic system that we can think of. So individually we can write the Hamiltonian for electron number 1 and electron number 2, and then we can express the overall Hamiltonian as this capital H, and so for the moment we are ignoring the term that is for interaction of the two electrons. So up to this it is simple, we are considering them as each electron separately, and then writing their wave Hamiltonian, getting the writing their wave function as psi r1, and which is an eigenfunction of this wave function is an eigenfunction of h1 and gives you energy E1. In a similar fashion, we can think of, we were writing for electron number 2, which the wave function will be psi r2, which will be an eigenfunction of Hamiltonian 2, and the energy that we get when we solve it will be represented by E2. So when we write this in a combined way, uh, so psi 1, psi r2, so both the electrons, and the combination, the multiplication of the two gives you psi r1 r2. So this is your eigenfunction with h, this one, this h is written over here. Okay, so उसका आइगन फंक्शन है जो इंडिविजुअली जो मल्टीप्लाई करके जो ओवरऑल वेव फंक्शन आ रहा है, that gives you the, so this is how we can start thinking about it. So h, this is eigenfunction of psi, and psi we have imagined as some multiplication of two terms, psi r1 electron 1 electron 2 for electron 1 electron 2 electron number 2. So that's how, so these two things and combined together they give you psi r1 r2. So this is what we have learned, and we are using this over here, further expanding the terms. So h1 operates on psi on all this. So you can write, expand this equation, expand it, write the two terms separately. So h, the first Hamiltonian, operates on psi r1 r2, the two things, and then second h2 operates on this. So remember, this one is written, why we are writing like this, because psi r2 is eigenfunction of h2. Okay, this is an eigenfunction of psi 1. So these two things you remember. So when you write it this way, it becomes easier to understand. So this one must be equal to E1 psi r1, and this one on this side would be equal to h psi is equal to E psi, energy of second electron. This will give you psi r2. So like this. So just expand this, use this technique, and so in this way you can further expand, see the writings. So you get this thing translated to this. Okay, and similarly h2 psi, this is now, you can write it here like this. So when you write it like this, you can get an expression where e1 plus a2 can be collected, because other two terms, multiplicative terms, are common to both. And so you can, इसके बाद आप, you get E1 E2, it will be the total energy E psi. So E1 plus E2 is the total energy E, where E is E1 plus E2. Okay, so we were here. Sorry for the break. Okay, I'm audible. Okay, so देखा हमने क्या किया, हमने पहले ये लिखा हैमिल्टोनियन R1 R2 साई को एक्सपेंड किया, which was a combination multiplication of the two wave functions. ठीक है, एक दोनों इलेक्ट्रॉन के लिए, और फिर हमने इस इक्वेशन को फर्दर एक्सपेंड किया. इसमें ये देख रहे हैं कि हम वो पेयरिंग अच्छे से आप कीजिए जो कि आइगन फंक्शन है, एक साई आइगन फंक्शन है, साई r1 आइगन फंक्शन है h1 का, इसको इसके साथ कनेक्ट कीजिए और ये वाला इधर कीजिए, तो आपको फिर आसानी हो जाती है. यू राइट इट एज E2 psi r2 and this one becomes E1 psi r1. So finally you get it like this. So the total energy E1 plus E2 is written as E1 plus E2 is the total energy. So so this is how we represent the orbital approximation through uh, simply writing it as a Hamiltonian for the electrons, each one of them at a time, and then combining them together. So E1, E2 is your so this is the result that we needed. Okay, so if the electrons interact, and this is a fact, so this one what we have written over so far is considering that the two electrons do not interact. If they interact, then this one has to be improved further. Otherwise, yeah, you are far away from the reality. Okay, so but still, the way it is a simple approach, and it is reasonable, and it is still applied in this way to understand the atoms. So this becomes a starting point only. So first you try to understand in this way, then we add that part, the interaction that happens. So this, what does this, how does this help you? So it is able to, you are able to talk about the uh, uh, configurations, how the electrons are arranged in their ground state. So if you start writing the hydrogen, you just like considering them, the ground state of hydrogen was 1s1. In a similar way you can think of जो पहला इलेक्ट्रॉन है वो तो उसी में जाएगा 1s में. The second electron, you can imagine, when we are talking about helium, it has 2 electrons. So the second electrons will be uh, second electron has to be added next to the orbital. So it goes to the same orbital 1s. There is a difference between the 1s orbital of hydrogen and 1s orbital of helium. In what way? How they are different? How they will be different? Charge Z is different, so it will be drawn inwards. In case of helium, because the number of protons have increased, now they will attract the electron much strongly, right? So there will be greater attraction between the two protons. Now you have doubled the number of charge at the nucleus, so that will attract the electron strongly, and it will move closer to the nucleus. So that's why we say that the orbital, 1s orbital is more compact than that in hydrogen. कॉम्पैक्ट कहते हैं ना किसी चीज को जब एकदम छोटी सी जगह में बहुत सारी चीजें रखी होती हैं, we say that it is compact, one unit. If it is more spread out, that then that is so in comparison to hydrogen, where you had only one proton, now you have two protons, and the same one is orbital, which we have imagined as one electron wave function, assuming one electron has standing wave, and then you make the wave function. So that because of that increased attraction, now it is pulled closer to the nucleus, and that's what we mean when we say that orbital has become more compact in case of helium, as when we are comparing it with hydrogen. हाइड्रोजन के कंपैरिजन में हीलियम का जो 1s ऑर्बिटल है वो ज़्यादा कॉम्पैक्ट हो गया है. That's what we say here, right? So the second electrons is goes to the first 1s orbital, 1s2, so it becomes 1s2 ground state. In case of lithium, the first two is okay, going to 1s. Where we put the third one? Here comes the role of Pauli's principle, okay, which says that it was given by Pauli, and actually there is जैसा आपको हाइजेनबर्ग अनसर्टेनिटी प्रिंसिपल के बारे में बताया गया था कि there is a more general principle of uncertainty in mathematics between two operators. between two observables. So similar to that, you also have a general principle of uh, Pauli's principle, which is known as Pauli's principle, and Pauli's exclusion principle, which you have been taught in class 11th and onwards, is a special case when applied to electrons. Okay, so we are more first learning about the special case that you already know, and then we go to the general principle of Pauli's. So the Pauli's principle tells you no more than two electrons may occupy any given orbital, and if two occupying one orbital, their spins must be paired. Spin pairing, what does pairing of spin means? स्पिन पेयरिंग का मतलब होता है एंगुलर मोमेंटम का जीरो हो जाना. ठीक है, ये ध्यान दीजिएगा. The two angular momenta of electron 1, the angular momentum of electron number 1, the angular momentum of electron number 2, the spin angular, I am talking about spin angular momentum, right? दोनों का spin angular momentum vector opposite होना चाहिए, such that they cancel out. ठीक है, तो when you show it like this, paired spins, it is denoted like this: paired spin, zero net spin angular momentum. Then only we say that it has been paired. Okay, now what does this was only the z component, remember, this was the z component plus half, and this was the minus half, the z component of the angular momentum that we are showing vertical lines. Okay, now we also know, because of the uncertainty principle, this we have to show on the vectors have to be shown on the respective cones. They are oriented along that cone such that the resultant spin is zero. कैसे? अब बताइए, पिक्चर देख के बताइए, क्या ये पेयर्ड स्पिन पेयर्ड सिस्टम है? हेलो, हाँ, ये स्पिन पेयर्ड सिस्टम है. पिक्चर देख के बताइए, क्या ये स्पिन पेयर्ड सिस्टम रिप्रेजेंट हो रहा है? नो, नो, शॉक, शॉक लगना चाहिए. दिस इज नॉट अ स्पिन पेयर्ड सिस्टम, दिस इज रॉन्ग. देखिए, एक वेक्टर ऐसे पॉइंट कर रहा है, दूसरा वेक्टर ऐसे पॉइंट कर रहा है. रिजल्टेंट बताइए, किधर जाएगा रिजल्टेंट? समवेयर हियर. नेट मोमेंटम होगा. दिस इज नॉट अ करेक्ट रिप्रेजेंटेशन ऑफ अ spin paired system. The angular momentum, spin angular momentum is finite. It is not cancelling out. आप जो देख रहे हैं, आप बस अधूरा सोच रहे हैं. आप सोच रहे हैं कि ये तो प्लस हाफ हो रहा है, ये माइनस हाफ. अरे वो तो सिर्फ z कंपोनेंट था. ठीक है, बाकी सब तो है, दिख नहीं रहा. ये टोटल जो एक्चुअल एंगुलर मोमेंटम है वो कौन है? वो जो कोन पे रखा हुआ है, ये जो कोन पे डाला है एरो, दिस वन इज योर एंगुलर मोमेंटम, राइट? यू डोंट थिंक इन टर्म्स ऑफ द z कंपोनेंट ओनली. ठीक है, ध्यान से देखिए. अगर हमने एक कोन पे वहां रखा और एक को यहाँ रखा, then it is not cancelling out. They are not, the sum of two is finite here, right? Two vectors add up, non-zero. So that's why I'm saying that this is wrong. ठीक है, these are final points which many books skip. अब देखिए, this is second arrangement. So is it correctly represented spin paired? Yes, this one is correct, because now the two vectors, one is pointing, this is my spin angular momentum vector, this is another spin angular momentum vectors, both are cancelling out, and this net momentum is zero. So whenever you are showing, अब आप as a mature master students, whenever you are asked to show the spin of electrons, the paired spin, you will show it like this. Place it on the cone. If one of the vector is pointing in a specific direction in the cone, the other on the downward cone will be pointing straight opposite to it. It must cancel out. Okay. So the first spin angular momentum vector can be placed anywhere on the cone, but then the other angular momentum vector must be placed on the second cone downwards, such that it exactly cancels out. So two vectors. So you have to think of in this manner by two vectors that lie at indeterminate position on the cone shown here. But as if one of them is shown to be in some direction, the other one must point opposite to it, such that the resultant is 0. ठीक है, तो ये वाला सही रिप्रेजेंटेशन है. पहले वाला जो आपने देखा ये गलत था, ये स्पिन पेयर्ड सिस्टम के लिए नहीं है. दिस वन इज ट्रू फॉर द स्पिन पेयर्ड सिस्टम. सो फंडामेंटल्स को स्ट्रॉन्ग कीजिए, राइट. नहीं तो स्पिन पेयरिंग की बात करते हैं कुछ भी बस वो डब्बे में ऊपर नीचे दिखा देते हैं. आप देखिए कि जेड कंपोनेंट तो वही है जो यहाँ पे था, वैसा ही है. जो ऐसे था जेड कंपोनेंट तो उतना ही है, नहीं चेंज हुआ. लेकिन बाकी सारा अब हमने सही कर लिया है ना. दिस इज स्ट्रेट अवे कैंसिलिंग आउट द फियर. द एक्स वाई कंपोनेंट्स आर आल्सो कैंसिलिंग ईच अदर. So exclusion principle is applied to structure of these multi-electronic systems when we try to understand them. It is also helpful in accounting for the periodic properties and molecular structure. So it was Pauli, पूरा नाम Wolfgang Pauli, who tried to account for this. So it originated, उसका भी experimental origin है. It originated from certain experiments, spectroscopic experiments. When spectrum of helium was analyzed, he found that certain lines are absence of certain lines. That led to this principle. Okay. And he derived a more general form. उसने इलेक्ट्रॉन के लिए सोचना शुरू किया, and he derived a very general form of this principle, which takes into account the spins of the particles, all fundamental particles, not just electrons. सबके लिए बनाया उसने, और तब उसने एक पेयरिंग वाली ये बात कही. Electron is a special case of that principle. So this is Pauli's exclusion principle applies to any pair of identical fermions. Fermions का मतलब s particles having s is equal to half. ठीक है. The spin quantum number s is half, so it applies to all such. So it applies to neutrons, it also applies to protons when you are arranging them in nucleus. Okay, so what it tells you, so anything with half integral spin. It also applies to nuclei when we view them as a single one unit particle. That's sometimes we'll talk about it later in nuclear. When we talk about nuclear structure, then we talk about treat the entire nucleus, the combination of neutron and protons, as single particle, single entity, and we assign certain spins. Then in that case, if it is half integral spin, again the fermions, we treat them as fermions, just like electrons, proton, neutrons, and that kind of thing, like 35Cl. So that is something we will discuss when we go to that part. When you go to spectroscopy, rotational, vibrational spectroscopy, you will have to consider those things. So right now we can stick to what we have been learning. We are talking about hydrogen atom. Okay, and so what this general principle tells you is this. The general statement of Pauli's principle, more general statement is this. ये थोड़ा डरावना है, but you can still break through, मतलब you can decode it. That was more general, sorry, selective special case for electron and all other fermions. So this is what it says, more general statement. When the labels of any two identical fermions are exchanged, the total wave function changes sign. इसी चीज को रिप्रेजेंट करके वो वहां पे लिखा गया था कि the spin must be the total wave function will change sign when all other radial wave function, angular wave function, everything is same. The spin wave function must change sign. You can write a wave function for spin also, and that gives you total wave function. So total wave function means spin and orbital. So what we are writing, total, when we say total wave function, it is combination of two things: orbital wave function and multiplied with you have spin wave function. Total wave function is a combination of these two things. Okay, and this, you know, orbital wave function we have already separated into r, y, angular, and this phi. So this already we know. Orbital wave function is split into angular and radial. So when I am placing electron in 1s orbital, the entire set of orbital wave function is same, and so the total wave function, that as stated over here, will be different when spin wave function is different, right? So that change in sign will happen only when the spin wave function representing the opposite spin angular momentum on opposite cone is that we write equation for that. So this is what is implicated. So spin wave function, which is represented as this is for two types, we write it as alpha, beta. For s is equal to half, sorry, ms is plus half, 1 by 2, and we write it as beta if it is ms is minus 1 by 2. Sorry. So beta is written for minus 1 by 2 ms values. We are talking about ms, the z component, right? So that is the difference. The spin angular momentum never changes, right? There is change in the z component. Either it will be plus half or minus half, h cross, and so on. So that's why this must change to have overall. Let me tell you what is. We are talking about when the labels of any two identical fermions are exchanged. So exchange of labels, what does that mean? Just a moment. So when we talk about exchange of labels, so अगर हम जिसको इलेक्ट्रॉन 1 कह रहे थे उसको इलेक्ट्रॉन 2 कर देंगे, तो वो चेंज ऑफ लेबल्स होगा. So suppose this is our nucleus, and around that we have electron number 1. We have, suppose we have electron 2, 1, 2. If this one was R1, this one is R2. So now change of label means that the second electron is change of labels. Exchange of labels means this will becomes 2, electron number 2 comes over here, and the electron number 1 goes over here. Exchange of, if you exchange the two places for the two electrons, and then what will be the sign of wave function? That sign of wave function must change. Okay, so that's what it says. So overall wave function must become negative. Whatever if it was positive earlier, it will become negative, and vice versa. If it was negative, it will become positive. So that must happen in case of electron. When we think of, so here we are talking about two electrons in the same or electron 1 and 2, and we change the labels. In this we are visualizing electron number 1, electron number 2 in the same thing, okay, at distance r1. In the same case, in case of helium, this is what I start visualizing, and we exchange the label 1 becomes 2 and 2 becomes 1, exchange of labels. So 1 2, so we are, the two electrons are being exchanged. So in that case the wave function must change sign, whatever we have written. So if that, so how can we make it true? ये तभी होगा जब स्पिन का जो z कंपोनेंट है, स्पिन एंगुलर मोमेंट का, वो एक का पॉजिटिव दूसरे का नेगेटिव हो, ओके। तो ऐसा कैसे होता है वो भी हम थोड़ा डिटेल में भी देखेंगे. सो वी विल स्टार्ट राइटिंग दिस इक्वेशंस. सो just a minute, let me discard this whole thing. So what we have just discussed, exchange of labels and total wave function of fermions, that is electron is a fermion, that must change sign. By the way, the second part of the statement, general statement, talks about the bosons. When two identical bosons are changed, any two identical bosons, their wave function retains the sign. ये आगे चल के यूजफुल होगा. We will later on use this concept in rotational and vibrational spectroscopy. So that part, second part, we are leaving for the moment, but keep in mind, total wave function is what I just explained to you. It is the entire wave function which includes spin and the orbital part. Orbital wave function, spin wave function, both. So when we are writing the wave functions, Pauli's exclusion पे psi 1 2, two electrons are there. So electron number 1, electron number 2, the distance. So actually this principle that we are talking about has its roots in theory of relativity. Again, and this is a fundamental thing of fact of nature. This happens in so many particles. This exclusion principle applies to the general statement of Pauli's principle applies to all the. So it is about fermions and bosons, not just electron, protons or anything. So bosons में आपका photon भी आ जाता है, बहुत सारी चीजें आ जाती हैं. So like that, so it applies, it all pervasive statement, सब जगह apply होगा. So but we are focused on thing, the wave function must change sign if we interchange the labels 1 and 2. So I just showed you what this interchange of labels means. So you bring the electron number 2 in place of electron number 1. So 1, we say that labels have changed, and then the description. So in that case, so this is what it means if we write in terms of equation. So 2 goes in place of 1, 2 goes in place of 1, 1 goes in place of 2, right? So when we exchange the place, the sign of wave function will turn negative, or positive to negative. So that kind of thing should happen. So this is what we mean by, I think that happens. Suppose the wave function psi. So in the orbital approximation, we write overall special wave function as psi 1, psi 2. This is the combination. We start with this equation. So this is the orbital part. This is only the orbital part, orbital wave function. Okay. We have to also include the spin. We need to include the spin, and so for that we need to write in terms of alpha 1, just wave function of electron number 1, the orbital wave function of electron number 2. In a similar fashion, we can write the spin wave function of electron number 1, the spin wave function of electron number 2, and so on. So alpha beta, we can imagine 4 such combinations. when both the electrons have alpha state, that is plus half, ms is plus half. When both the electrons are in beta state, that is ms minus half. So alpha state means ms, the z component is plus half, and the other case it is minus half. And then there can be combinations when electron number 1 is upspin, electron number 2 is downspin, and vice versa. The electron number 2 is having alpha and beta like this. So this is what you talk about electron 1 being upspin, this is being downspin, 1 2, और यहाँ पे हम क्या कर रहे हैं अप एरो, बट यहाँ पे ये 2 है और यहाँ पे ये 1 वाला इलेक्ट्रॉन बीटा फंक्शन. So that's what we are trying to show here when we are writing this. This is what my imagination is when I am writing this in this manner. So ये हो गया, this is my, so all these 4 things that we have visualized, 1 2 3 and 4, these are spin wave function. Combining these two, we will get the overall total wave function for the electron. So okay, so so the Pauli's principle. So spin states, what we are talking about is there is also a problem here. We cannot be so precise that we can say the electron number 1 is having, because of the uncertainty, we are not sure whether electron number 1 is upspin or whether electron number 2 is upspin, whether electron number 2 is downspin or 1 is downspin. So you cannot be so precise, and you have to account for uncertainty also. In that case, we can write it as a linear combinations. Spin states can be written as linear combination, and then taking under root half. So linear combination, you apply the normalization constant. So normalization constant comes over here. So finally you can have 2 combinations that you can see: alpha, beta, 1 2, 1 2, beta, alpha, alpha, beta, beta, alpha, 1 2, 1 2, like this. So in the middle you can see the plus sign here, in here you are seeing the minus sign. So these are 2 combinations. So any wave function, we have learned in from the fundamental principles of quantum mechanics that uh, you can express wave function as a combination of 2 separate wave functions, multiple wave functions like that. So that is the way we break it down and make it things easier. So then you are accounting for the uncertainty in the which one is having one of alpha and which one is beta, and that you can write it. So these are 2 combinations that we can think of. We can write it. So 1 2. So one is representing the plus in phase, and other one the out of phase combination of the 2, the basic function alpha 1 beta and beta alpha. So we are using these things to combine here and write it this way. Okay, product of, so total wave function is the product of all this orbital part and the spin states. So 4 spin states are there now. Psi 1 psi 2 remains same, but we can write alpha 1 alpha 2, beta 1 beta 2, and then the 2 combinations. Okay, so total we can think of 4 different total wave function. 4. Psi 1 psi 2 is constant in all of them, that is appearing all in all of them. Rest we are thinking both having alpha, both having beta, both the 2 electrons spin, and then the combination of 2, which is represented over here. Now which one of these 4 is the correct representation? That's the question to be asked. Now we also learn about simplifying, writing shorthand notation. So we call this wave function as spin orbital. When we are writing the two components, the orbital part, the spin, and then combined wave function, it is called spin orbital. And the combination, if you are writing for the electron number 1, wave function orbital part is psi, wave function for the spin alpha, then we write it like this. And further we can simplify and write it like taking alpha as the superscript, writing as, so this is a simpler shorthand. So this is a shorthand notation for writing that. तो सिंपल तरीके से लिखने के लिए उसको थोड़ा, सो यू मस्ट अंडरस्टैंड द पैटर्न. द स्पिन पार्ट, जो स्पिन वाला पार्ट है उसको हमने सुपरस्क्रिप्ट कर दिया है बस. साई अल्फा, साई 1 था, उसके ऊपर से अल्फा कर दिया, तो इसका मतलब है इलेक्ट्रॉन विथ साई एज द वेव फंक्शन एंड अल्फा एज द स्पिन वेव फंक्शन, ऑर्बिटल वेव फंक्शन एंड स्पिन वेव फंक्शन. सो ये आप इस तरह से लिख सकते हैं. सो in general we write spin orbital wave function as electron number, the nth electron having alpha as the spin state and psi as the orbital state. We write it like this. If it is in beta state, we write beta as the superscript. Okay, so we can then write this thing over here. एक मिनट. So अमन सहाय, हैंड्स अप. क्या हुआ? वॉइस इज नॉट क्लियर. ओके. ओके, मे बी नेटवर्क इशू ऑन माई पार्ट हो सकता है. हाँ, थोड़ा सा टेक्निकल प्रॉब्लम हो जाता है. तो हमने शॉर्ट हैंड नोटेशन लिखना शुरू किया. और sorry, हाँ, सो अब हम चार तरह से टोटल वेव फंक्शन को लिख सकते हैं. और इसको फिर शॉर्ट हैंड नोटेशन, जो एक स्पिन ऑर्बिटल कंबाइन करके जब हम लिखते हैं, तो उसमें हम इस तरह से यूज करते हैं. ये फॉलो करेंगे. जो स्पिन स्टेट है उसको जस्ट साई के ऊपर सुपरस्क्रिप्ट कर देना है. जैसे इसमें बीटा अगर स्पिन स्टेट है तो बीटा को इसके ऊपर साई के ऊपर सुपरस्क्रिप्ट कर देना है. nth इलेक्ट्रॉन हैविंग बीटा स्टेट, स्पिन स्टेट एंड साई एज द ऑर्बिटल स्टेट. तो ये कंप्लीट डिस्क्रिप्शन हो जाता है. सो व्हेन वी आर राइटिंग दिस, इट इज द सेम थिंग दैट वी वर राइटिंग हियर. ये यहाँ पे इतना लंबा सा जो दिख रहा था वो एकदम छोटू सा हो जाता है यहाँ पे. जो यहाँ पे इतना बड़ा सा ऐसे दिख रहा था वो ऐसे करके बीटा को आप ऊपर सब्सक्रिप्ट कर दीजिए, तो दिस वन बिकम्स लाइक दिस, सिंपल, राइट. सो we have to account for the Pauli's principle, which says that signs must change when the label is changed. So अब लेबल चेंज करने का यहाँ पे हम देखेंगे कि कैसे ये वाला किस किस, इन चारों में से कौन सा सेटिस्फाई कर रहा है, कौन सा नहीं कर रहा है. जो सेटिस्फाई करेगा वही एक्सेप्टेबल सॉल्यूशन होगा, जो एक्सेप्टेबल वेव फंक्शन होगा. So the Pauli's principle says that exchanging the labels 1 and 2 converts the factor. So if you are writing 1 psi 1 psi 2 like this, it will become, the orbital part will become psi 2 psi 1 like, now like this. However, you will note that whether you write psi 1 with psi 2 or psi 2 with psi 1, the result is same. Result is same, and multiplication of the orbital part has no effect on the change of the value of product, change of sign or values. Okay, so the orbital part does not affect the sign. That's one thing. Now we look for the same thing like this: alpha 1, alpha 2. Now whether we interchange with 2 1 1 2 and beta 1 beta 2, again the same thing. This will not change, so we reject. Based on this, we reject, just a moment. So what we have just discussed, the product, just can't get out. What we have just discussed, psi 1 1 psi 2. So this is same, exactly the same as psi 2 for electron 1 and 2. So this one, these things, so orbital part is not, as we see here, the product is same. So interchanging the labels, so this is what we mean by interchange of labels. And under the interchange of labels, मतलब इलेक्ट्रॉन 1 इलेक्ट्रॉन 2 की जगह कर दो, 2 को 1 की जगह कर दो, और तभी इंटरचेंज ऑफ लेबल्स पे वो साइन प्रोडक्ट अफेक्टेड नहीं हो रहा है. द सेम थिंग अप्लाइज when we are writing the spin state in this manner. If we are writing the spin state in this manner, like alpha 1 alpha 2, when we change the labels, the product will be same: alpha of second and alpha state of alpha of 1 electron. Product is same, nothing. So these are not, so sign remains same in these cases for 1 and 2. So 2 are rejected, these two, this one crossed out, this one is, this one is also crossed out. These are not the correct solution. Now we are left with the two solutions, two wave functions in the lower panel, which are the linear combinations. Now what you see, linear combinations, just, so the linear combination also you can think of, you can start writing that also. So first two out of four we have rejected the two. Now we are left with two which are appearing as combinations of the two spin states, because we were, as I told you, we are uncertain about the whether electron number 1 is alpha state or beta is alpha state, so we write the combination. And so this is, you can see again, when we are writing this in this manner, you change the label 2 1, it will be the product, as we said, alpha beta, the product is alpha 2 beta 1, the product is like this. So this gives you, in case they are addition, there is no change, the sign remains same. Sign of the wave function has the value, the sign, nothing has changed. So third one is also, third one was about it. So third one, we are rejecting the third one as well. Sorry, कहाँ गया वो जो अभी लिखा था. So we have rejected this, and this one is also rejected. Last one, we are left with the last one. Whether it is the correct solution or not, we will just realize here. So now the final thing is this one: change the label. So we were writing this as 1 2 and 2 1. So if you are writing it like this: alpha 2 beta 1 minus beta 2 alpha 1. If you change the labels, make it 1 and 2, 1 2, then what will it will be? It will be a negative sign here as shown, and overall sign changes. It is just like you are writing for a moment. So if suppose this is represented as A, if this one is represented as B, let me just take this thing here. just a moment. What we are trying to say. So if suppose this one is represented as small a, this beta 2 and alpha 1 is represented as b, small b, then this one is the same thing as, so jab 1 electron number 1 is beta state, this is the thing, alpha 2, so this is your a, and this beta, the second electron is in beta state and alpha state, so this one is b. So if the top one was, so just imagine in this way, if y was equal to a minus b, y1, and if you change the labels, like if you write b minus a, if y2 is b minus a, then y1 will be equal to minus b minus a, which is minus y2, like this. So this is what we are trying to express here, कि अगर ये प्रोडक्ट एक भी है, अल्फा जब इलेक्ट्रॉन नंबर 1 अल्फा में है और इलेक्ट्रॉन नंबर 2 बीटा स्टेट में है, तो इसका एक प्रोडक्ट होगा। जब इलेक्ट्रॉन नंबर 2 अल्फा में उल्टा अगर हम कर दें, अल्फा स्टेट में 2 वाला है, बीटा में 1 वाला है, तो इसका एक प्रोडक्ट होगा ए। तो अब ये a माइनस बी है, यहाँ पे b माइनस ए हो जाएगा, तो साइन पूरा बदल जाएगा, ठीक है, विच इज हैपनिंग इन दिस केस। सो सिंपली इमेजिन दिस 1 2 and then you just try to rearrange equation, you will find that it is happening, turning out to be true. So the last one satisfies this condition. जो भी हमने चार imagine किया, so we have imagined 4 different functions, and out of which only one is turning out to follow the Pauli's principle, that when the labels are changed, the sign changes. One exchanged with 2, sign changes. ये हो रहा है, sign of the overall wave function is changing. So this one is correct, all others were found to be incorrect description. ठीक है, so this is how we implement these things, and yeah, so this is just the thing. So finally we have arrived at that this one is the correct. So it is when we take into account the fourth combination, the alpha beta, beta alpha. When we change the labels, 2 goes to 1, 1 becomes 2. In that case, the sign of the wave function, spin wave function, is changing, and so the overall wave function sign is also changing. So total wave function is changing, and that explains why. So we say that this function is antisymmetric. मतलब सिंपल कहें तो पॉली प्रिंसिपल ये कहता है कि इलेक्ट्रॉन का जो ओवरऑल वेव फंक्शन होगा, it should be antisymmetric. Antisymmetric wave function is something when you change the labels, the sign changes. Okay, so under the particle exchange, or we say when we exchange the particle, मतलब इलेक्ट्रॉन नंबर 1 2 की जगह पे, 2 वाला 1 की जगह पे चला गया, तब साइन पूरा बदल जाना चाहिए. In other words, we say that wave function should be, total wave function should be antisymmetric for electron. Wave function antisymmetric for electron. That's what we want. Okay, so just like we say that something is odd function, in a similar way you can see that there should be a change in sign it should behave in antisymmetric manner. And so what we have seen just now, out of four, only one has survived. That has spin pair combination of alpha and beta together. So that's what tells you. And this part was called the special Pauli's exclusion principle, special case of Pauli's principle. Pauli's exclusion principle is a special case of more general Pauli's principle, which we have just seen. Hmm. So, uh, if there are orbitals in which, when you are placing electrons, say three degenerate orbitals, p orbitals, even then that if the electron spin is same, even then you will find that one of them, the orbital part is changing, and that one gives you the antisymmetric nature. So overall wave function is antisymmetric, even though if in some case, just like imagine a px and py orbitals, you are placing two electrons, the spin state is same, but the orbital part will be different, such that overall there is change in the sign of the wave function. So okay, so next part we'll discuss in the next class. This is about penetration and shielding, typically observed in multi-electronic system, and that changes the degenerate energy of the system. The degeneracy is lifted. So that those things we will discuss in the next class. Okay, and how we can relate the shielding with the orbit that probability diagram. The radial probability diagram is crucial. I told you we'll be returning back to the radial probability curves for explanation of penetration and shielding. That we will do in the next class. So that's all.